In this video, we will discuss who won the Nobel Prize in Physics in 2025 and the reasons for their award, explaining all the details. But before delving into this topic, let's clarify a few important aspects. An electron exists as a cloud of possibilities, called a probability cloud. This cloud can take different shapes depending on the energy state of the electron. Scientists describe each of these forms using a so-called wave function, with each form corresponding to its unique wave function. Well, let's begin. Look around. Everything you see is made of atoms, and around each atom are electrons. Now imagine you have a special particle detector that allows you to locate one of these electrons in space. When we discover it, we see a simple picture, a small glowing dot on the screen. This is how we usually imagine an electron. But here is the strange truth. It looks this way because we measured it. As soon as we observe the electron, it takes on this neat particle shape. However, before discovery, it is completely different. It does not appear as a point or a sphere. In fact, it exists as a cloud of possibilities, something like blurred smoke scattered in space. This is what scientists call a probabilistic cloud. It is a mathematical description that shows us the chances of finding an electron in various locations. But many scientists believe that this is not just a mathematical concept. This cloud may be physically real, representing how an electron truly exists until the moment of observation. Even more fascinating is that this cloud is not empty or imaginary. It carries the charge of the electron, its energy and mass, although it has no fixed shape or boundaries. And at that moment, when we take the measurement, something amazing happens. All these possibilities merge into a single result. A scattered cloud suddenly focuses at a single point, and at that moment, the electron appears in reality, the very small point we see on the detector. Now, as we know, electrons behave like probability waves until the moment of observation. Let's imagine an electron purely as a wave, not as a tiny particle. It is said that atoms have different energy levels, and electrons are often described as occupying these levels. However, in reality, there are no physical layers or shells around the atom. These energy levels are different ways of distributing the wave of probability of an electron, called the wave function, around the nucleus. Let's consider the hydrogen atom as an example. In its lowest energy state, or ground state, the electron wave spreads evenly as a spherical cloud around the nucleus, like a soft glowing mist concentrated at the center. When the electron absorbs energy, an interesting event occurs. His wave does not turn into a faster moving particle. Instead, the entire cloud expands and changes shape. The new, larger cloud represents an electron in a higher energy state. Between these states, there are thin, invisible zones called nodes, where the probability of finding an electron drops almost to zero. You can imagine them as voids between different patterns of standing waves, like silent sections on a vibrating guitar string. If an electron receives even more energy, its wave pattern becomes more complex. The cloud can stretch and form petals, resembling a three-dimensional flower, with petals pointing in different directions. These formations are called pp orbitals. For example, a double-tailed orbital oriented along the x, y, and z axes, each positioned differently in space. Thus, when scientists say that electrons jump between energy levels, they do not mean that particles simply move from one orbital to another. In reality, a change in the shape of the electron's wave pattern occurs. It reorganizes into a new stable form that perfectly fits the potential field of the atom. Now let's consider an interesting phenomenon called quantum tunneling. Imagine an electron in a hydrogen atom. In a stable state, its probability of being in the cloud is roughly spherical and concentrated around the nucleus. This cloud is held close to the nucleus due to the electrostatic attraction between the negatively charged electron and the positively charged nucleus. Scientists often depict the binding force between the nucleus and the electron as a kind of wall called a potential barrier. This graph shows the probability of finding the electron in the ground state of a hydrogen atom, where its probability cloud is spherical. You may notice that the probability of finding an electron gradually decreases as you move away from the center. But here's an interesting point. If we place this wave function inside a potential barrier, you will see that at the edge of the barrier, the wave does not drop sharply to zero. Instead, it stretches slightly beyond the wall, indicating that there is still a small chance of finding the electron beyond the barrier. This is surprising, as according to classical physics, the electron lacks the energy to overcome the barrier. Nevertheless, in a truly quantum sense, the wave of the electron penetrates through the barrier. This strange yet real effect is called quantum tunneling by scientists. Scientists use this amazing quantum effect to extract electrons from atoms without providing them with the full energy needed to overcome the barrier. How do they do this? They apply a strong electric field to one side of the atom. Usually the nucleus is at the center, and the electron's probability cloud is evenly distributed around it. But once the electric field is turned on, the negative electron cloud is slightly attracted towards the positive part of the field, while the heavy positively charged nucleus shifts slightly in the opposite direction. This leads to the atom becoming slightly tilted or polarized. One side now has a denser cloud of electrons, while the other has a less dense one. Due to this distortion, the potential energy of the atom, which scientists call the potential barrier, becomes inhomogeneous. On the side where the cloud of electrons is attracted, the barrier becomes thinner and lower. The wave function of the electrons, which usually fades smoothly at the edges, now stretches slightly in that direction, penetrating the area beyond the barrier. Thus, part of the electron's probability cloud seeps out, even if it lacks enough energy to escape in a classical manner. Now let's talk about the Nobel Prize in Physics for the year 2025 and see how scientists turned quantum tunneling into real applications, including its use in creating quantum computers. The prize was shared between John Clark and Michael H. Devar and John M. Martinez demonstrated that quantum effects are not limited to tiny particles, but can also manifest in larger, carefully constructed systems. In practice, they used a tiny device called a Josephson junction in superconducting circuits. This junction is created by placing a very thin insulating layer between two superconductors. Usually, an insulator blocks the flow of electrons, but in a superconductor, electrons form pairs called Cooper pairs. All these pairs together behave like a single coherent quantum wave, similar to the probabilistic cloud of an electron around an atom. This quantum wave can actually tunnel through a thin insulating barrier. It is the same phenomenon we observe in atomic tunneling, when the probability cloud of an electron can extend beyond the binding force of the nucleus or potential barrier. Inside the Josephson junction, a superconducting wave exists in a potential well, similar to a probability cloud enclosed by an atomic nucleus. Here, a potential barrier is formed by a thin insulating layer. A quantum wave in connection can also take various forms when it receives energy, much like the different shapes of the electron's probability cloud around an atom. As we already know, due to quantum mechanics, a wave can occupy only certain energy levels or shapes within this potential barrier. In a state of lowest energy, the wave is compact and mostly resides within the barrier, with only a tiny part seeping into the wall, making the tunneling probability very low. At higher energy states, the wave stretches further, and more of its parts reach the barrier, increasing the probability of tunneling. Scientists can control the energy state or form of a quantum wave by applying microwave pulses with the precise energy needed to move it from one level to another. When the wave absorbs this energy, its shape changes, and it reaches a higher energy level. In this new state, the wave penetrates deeper into the barrier, making tunneling more likely. By controlling energy states and observing tunneling behavior, scientists can manipulate the quantum state of a superconducting circuit. The ability to control tunneling and energy levels allows Josephson junctions to function as quantum bits or qubits in quantum computers. The lowest energy state can represent 0, and the next one represents 1. Since a wave can exist in a superposition of states, it can be both 0 and 1 at the same time. Scientists use microwaves to shift the wave between these states and read tunneling behavior to determine the state of the qubit. This is how tunneling in Josephson junctions is used for storing, manipulating, and reading quantum information, which forms the basis of modern supercoherent quantum computers. These three scientists were awarded the Nobel Prize for creating special circuits. These chains allow electric current to behave strangely, characteristic of quantum mechanics. They demonstrated that even a chain made up of millions of electrons, large enough to be seen or touched, can still exhibit quantum tunneling, a phenomenon once thought to belong only to the micro world. Their experiments proved that such chains can absorb and emit energy in fixed discrete portions, like real atoms. By controlling these effects, they managed to create artificial atoms, human-made versions of nature's building blocks. These artificial atoms are now used to create quantum computers, ultra-sensitive sensors, and other advanced quantum technologies that could change the future. This video comes to an end. I hope you enjoyed it, and don't forget to share your thoughts on this discovery.